quantum gates, the real powerhouses behind quantum computers. We're going to break down how they actually work and why everybody's so excited about what they can do.
Yeah, it's a whole new world. We're not talking about the simple ones and zeros of your laptop anymore.
Right. It's like we're moving past that. So we've been digging into this analysis of how these quantum gates work, and it's fascinating. They're similar to the logic gates we already know, like, A and D or R, not T. But they don't work on bits. They work on these things called qubits.
Right, qubits. And those qubits can be in a superposition, basically a blend of states.
Yeah, this superposition thing, I mean, how do you even picture that?
Well, think about a coin spinning in the air, before it lands. It could be heads, it could be tails, but it's kind of both at the same time while it's spinning. That's kind of like a qubit.
So it's like this in-between state, this potential.
That's the power of it. It's harnessing that uncertainty. That's where the possibilities get really interesting computationally.
Okay, I think I was starting to get that. But how do these quantum gates, how do they actually manipulate these qubits, especially when they're in that, like, fuzzy in-between state? The analysis we've been looking at says something about unitary operators and matrices. I gotta admit, math isn't my strong suit.
Don't worry. You don't need to be a math whiz to understand the basics here.
Okay, good.
The key takeaway is that these mathematical representations ensure that operations in the quantum world, they're reversible.
Okay.
Which is huge in quantum mechanics. You can't just lose information in the quantum world. It has to be preserved.
So every action has to have a consequence, and you can always trace your steps back. It's like the quantum world has its own accounting rules.
Exactly. Now, I know you mentioned earlier that we were going to dive into different types of quantum gates. There's the single-qubit gates and the multi-qubit gates. Should we start with those single-qubit gates?
Yeah, let's start there. I'm really curious about the Pauli gates. They sound kind of like the rock stars of the quantum world. What makes them so special?
Think of the Pauli gates. There's X, Y, and Z, kind of like the not T gate in classical computing. But they have these extra layers of complexity. Instead of just flipping a bit on or off, they can do things like rotations and add in these things called phases.
Okay, so it's not just flipping the qubit. It's like they're adding some flair to it.
Exactly. Let's take the Pauli X gate, for example. Imagine you have this qubit, and we're picturing it as a sphere, like a globe. The north pole is state 0, the south pole is state 1. Now, the X gate, it's like holding a mirror up to that qubit sphere. It flips the state across the equator. So north becomes south, 0 becomes 1.
Okay, a complete flip, like a mirror image. I got that. Now, what about the Hadamard gate? The analysis said that's the one that actually creates the superposition, that spinning coin state.
Right. That's the one that takes a qubit that's in a definite state, like a 0 or a 1, and puts it into that blend of both states. It's not just flipping between poles, it's rotating our qubit sphere so that it's perfectly balanced between north and south.
So it's not just flipping, it's actually creating this entirely new state. And that's what gives quantum computers their advantage.
Exactly. Because now, that qubit isn't just one thing, it's both things at the same time. And that's what lets it explore a ton more possibilities at once. It's like, for certain problems, they can blow classical computers out of the water.
Okay, my mind's officially blown. So we've got these Pauli gates doing their flipping and rotating, and then the Hadamard gate creating this superposition. What about these multi-qubit gates? How do those work?
That's where we bring in entanglement, that spooky action at a distance Einstein was talking about.
Entanglement. Yeah, that sounds both ominous and very cool.
It is. So instead of just working on individual qubits, multi-qubit gates link the fates of multiple qubits together.
Right.
Let's take the CNOT gate as an example. It works on two qubits, a control qubit and a target qubit. If the control qubit is in state 1, then it flips the target qubit. But if the control qubit is in state 0, the target qubit stays the same.
So it's like a conditional flip. But how does that actually create entanglement? Where does the spooky action come in?
Okay, imagine you have two coins. Right. And no matter how far apart you separate them, when you flip one, you instantly know the state of the other one. They're linked. That's kind of like entanglement.
Oh, yeah.
So if we start with both of our qubits in a superposition, and then we use the CNOT gate, they become entangled. Measuring one qubit immediately tells us the state of the other, even if they're miles apart.
It's like they have this secret communication channel that breaks all the rules of physics as we know them.
Pretty much. And that interconnectedness, that's a key part of why quantum computing is so powerful. It's like, instead of doing things one at a time, you can work on multiple things at once. It's mind-blowing.
It really is.
Yeah.
But how do we actually build a quantum computer? I mean, how do you create these gates in the real world? I know the analysis mentioned something called quantum circuits.
You got it. Quantum circuits. They're kind of like these circuits in a regular computer, but They're built out of these interconnected quantum gates. And get this, a small set of these gates, called a universal set, can be combined to create any possible quantum operation. It's like having a basic set of Legos that you can use to build anything you can imagine.
So if you have this universal set of gates, you can build any quantum program. That's pretty amazing. But is it really that simple? Building an actual quantum computer? I mean, that's got to come with some serious challenges, right?
Oh, absolutely. Building these machines is one of the most difficult things we've ever tried to do. One of the biggest challenges is something called decoherence. Remember how we talked about how fragile those superpositions are? Well, any interaction with the environment can cause a qubit to lose its quantumness. It's like that spinning coin suddenly deciding to land on heads.
So it's like you're trying to build a house of cards in a windstorm.
Exactly. Maintaining that delicate balance of superposition is incredibly tough. And then on top of that, there are these errors. Quantum computers are inherently prone to errors. Even tiny fluctuations can throw things off.
So you have these amazingly powerful quantum gates that can do calculations beyond anything we can imagine, but they're incredibly sensitive, prone to errors. It sounds like building a practical quantum computer is like trying to herd cats, maybe even harder. Incredibly difficult, but if you could pull it off, it's game-changing.
You got it. It's a delicate dance, but the potential payoff is huge. And, researchers are making amazing strides in tackling these challenges.
Well, that makes me even more curious to hear about how they're doing that. I think we need a moment to just process all of this. This is mind-blowing stuff. Okay, I think I've had enough time to let my brain do a quantum reboot or something. So we've got these quantum gates, they're flipping and rotating, entangling qubits. It's a whole quantum circus down there. But I think I'm ready to dig into some of the specifics now. The analysis talked about these gates being represented mathematically as matrices. What's that all about?
It's kind of like a secret language for quantum computation.
Okay.
Those matrices, they describe exactly what transformation happens when a qubit interacts with a gate.
Oh, boy.
It's how we make sure everything stays consistent and predictable, even in this crazy quantum world.
Yeah, because it does seem pretty unpredictable sometimes.
Yeah.
I also remember something about those matrices needing to be unitary. Why is that so important?
Unitary is a big deal in quantum mechanics. It makes sure that the probabilities of all the possible outcomes always add up to 1. It keeps things from going totally off the rails.
So it's like you're not going to accidentally create a quantum paradox?
Right. It's a built-in system that keeps things in check. It also guarantees that every quantum operation is reversible. Like we talked about before, information can't just disappear in the quantum world. It has to be accounted for.
That makes sense. So let's get to some real examples. We talked about the Pauli gates before. Can we break those down a little more? Like what kind of transformations are they actually doing to our qubit sphere?
Absolutely. So remember we talked about the Pauli X gate, how it's like holding a mirror up to the qubit and flipping it?
Yeah, north to south or south to north.
Right. Well, the Pauli Y gate, it does a flip too, but it also introduces a phase shift.
A phase shift. I'm picturing our qubit sphere getting twisted.
You got it. Like rotating the qubit around a different axis. And those phase shifts, they're super important because they're what create these things called interference effects, which are a big part of how a lot of quantum algorithms work.
Okay, so the Y gate is flipping and twisting.
Yeah.
What about the Pauli Z gate? What's its thing?
The Z gate, it's the phase flip gate. It leaves the qubit alone if it's in state 0, but if it's in state 1, it flips the phase.
So it's messing with the internal rhythm of the qubit.
Exactly. It might seem subtle, but those phase flips are crucial. They're what allow for that constructive and destructive interference we were talking about, the kind that makes quantum computations so powerful.
Got it. So we've got the Pauli gates. They're doing all this flipping and rotating and shifting. Now let's talk about the Hadamard gate. That's the one that creates the superposition, that blend of states, right? How does it do that?
Think of it like shaking a snow globe.
Okay.
It takes a qubit in a definite state and turns it into a superposition of both states.
Wow.
Like our qubit sphere, it gets rotated so it's perfectly balanced between north and south. It's that spinning coin that hasn't landed yet.
So the Hadamard gate is the one that really unlocks the quantum weirdness.
Yep, you could say that. It lets us explore all these possibilities at the same time, and that's what gives quantum computers that exponential speed boost for certain problems.
Okay, I am starting to see why people are so excited about this. All right, let's move on to those multi-qubit gates, the ones that can entangle qubits. We talked about the CNOT gate before. Can we dig a little deeper into how that one works?
Sure. So the CNOT gate, or controlled NOT gate, it works on 2 qubits, right? A control qubit and a target qubit. Remember the two linked coins analogy? If you flip one, you instantly know the state of the other.
Yeah, that's a good one.
That's what the CNOT gate does. If the control qubit is a 1, it flips the target qubit. If it's a 0, the target qubit doesn't change.
So it's conditional flip, but how does that actually create entanglement?
Here's the cool part. Let's say both of our qubits start in a superposition. They're those spinning coins. Now, when you apply the CNOT gate, those two qubits become entangled. Their fates are linked.
Okay.
Measuring one qubit instantly tells you the state of the other one, no matter how far apart they are. It's like they're connected by an invisible string.
That is seriously mind-blowing. It's like they're communicating faster than the speed of light.
It really is remarkable. And this entanglement, it's essential for a lot of quantum algorithms. It's what makes things like quantum teleportation possible.
Quantum teleportation. That sounds like something out of Star Trek. But for now, let's stick with these quantum gates. Are there other multi-qubit gates besides the CNOT gate?
Oh yeah, there are quite a few. There's the Pauli gate, also called the CCNOT gate. It works on 3 qubits and acts like a conditional A and D gate. It only flips the target qubit if both control qubits are in state 1.
So it needs a double confirmation before it acts.
Exactly. And the Pauli gate is really cool because you can use it to implement all the classical logic operations, but in a reversible way. It's kind of like a bridge between the classical and quantum worlds.
So you can do classical computations, but within a quantum framework.
That's the idea. Then there's the swap gate, which, like the name suggests, swaps the states of 2 qubits. It might seem simple, but it's really important for moving qubits around within a quantum computer.
It's like the stage manager for our quantum computation, making sure everything's in the right place.
Exactly. And we also have the Fredkin gate, or the C-swap gate. That one swaps 2 target qubits only if the control qubit is a 1. It's useful for things like reversible computing and specific quantum algorithms.
Wow, we have this whole toolbox of quantum gates, and they each do their own special thing. It's amazing how they can be combined to make such complex quantum circuits.
Yeah.
But how do we know that we have all the gates we need? I mean, are there an infinite number of possibilities?
That's a great question. And actually, the answer is no. We don't need an infinite number of gates. Remember that idea of a universal set of gates? It turns out that with just a handful of basic gates, we can approximate any quantum operation, no matter how complicated.
Like those Legos again. You can build anything with a limited set of bricks.
Right. And the amazing part is that we can do all of this while still sticking to the fundamental rules of quantum mechanics, unitary, superposition, and entanglement. It's all woven into these quantum gates, which makes sure that everything is both powerful and consistent.
This is really incredible. I mean, it's mind-boggling to think about these quantum gates flipping, rotating, entangling, swapping, all orchestrated by these laws of quantum mechanics. But I have to imagine that there are still a lot of challenges ahead when it comes to actually building a useful quantum computer.
Absolutely. Building practical, fault-tolerant quantum computers is a huge undertaking. We still have hurdles to overcome.
Well, I'm ready to dive into those challenges and hear about what the future holds for this whole field.
Me too. Let's talk about it.
Okay, so we've really gone deep into this world of quantum gates, all the flipping and entangling. It's amazing. But building a real quantum computer, that sounds ridiculously hard. I mean, the analysis we've been looking at, it doesn't sugarcoat the challenges.
It really is one of the biggest technological challenges out there. Like, we're trying to control reality at the tiniest level.
Yeah, and the universe, it's not exactly making it easy. We talked about decoherence before, how those superpositions, they're so fragile, like the slightest bump can mess everything up.
It's true. It's like they're always on the verge of making a decision.
Right, like that coin that can't decide which way to land.
Exactly. That's why researchers are working so hard to shield these qubits from any outside interference. It's like building these super isolated fortresses using things like superconducting circuits that have to be kept colder than deep space.
Quantum monasteries, basically.
Yeah.
Shielding them from the chaos.
Pretty much.
Yeah.
Then on top of that, we have the errors, and those are a constant problem.
Yeah, those quantum gremlins.
Even with the best isolation, errors happen. It's like trying to perform brain surgery on a roller coaster.
So how do you even deal with that? Is there a quantum error correction or something?
You could say that. Scientists have come up with these things called quantum error correction codes. It's like a safety net for the computation. They encode the information redundantly across a bunch of qubits.
So even if some get messed up, you can still get the original data.
Exactly. It's like a backup system.
Mhm.
But even with all of that, building a quantum computer that's actually useful, it's still a massive task.
It sounds like it.
Yeah.
But let's remember why this is all so important in the first place. What are the things we could actually do with quantum computers, the things that make all this effort worthwhile?
The potential here is really huge. We're talking about revolutionizing whole fields like medicine, material science, even things like finance and AI.
Okay, so how would that work?
Well, imagine being able to design new drugs or materials, but at the molecular level, fine-tuning them for specific properties. In finance, you could have incredibly accurate risk modeling, and in AI, it could lead to totally new breakthroughs in machine learning.
It sounds like we're on the edge of a whole new technological era. And something you said earlier really struck me, the idea that quantum computing could actually help us understand the universe better.
Yeah, I mean, quantum mechanics at its core, it's a theory about how reality works at the most fundamental level. And by building these quantum computers, we're basically harnessing the weirdness of the quantum world to do calculations. Who knows what we might learn about how everything works as we get better at this?
It's almost like we're using technology to connect with the universe on a deeper level. So as we wrap up this deep dive into quantum gates, what's the one thing you hope people will take away from this conversation?
I'd say this. We're living at a really amazing moment in time where this whole new era of technology is becoming possible, and it's all powered by these tiny quantum gates. There are a lot of challenges ahead, no doubt, but the potential is incredible. And who knows, maybe by understanding these building blocks, we'll unlock some of the biggest mysteries of the universe.
It's been an incredible journey, really mind-blowing stuff. And to everyone listening, I hope this deep dive sparked your curiosity about the quantum world and all the amazing things that might be possible in the future. Thanks for joining us.